Have you ever wondered how artificial intelligence makes decisions, seemingly understanding complex patterns? While many AI models operate like black boxes, some offer a clear, intuitive window into their reasoning. Today, we're going to demystify one such model, the decision tree. Imagine a flowchart, but one that learns from data to make predictions or classifications. That's essentially a decision tree. It's a powerful, interpretable machine learning algorithm that mimics human decision-making by breaking down complex choices into a series of simpler ones. At its core, a decision tree is structured like, well, a tree. It begins with a single, root node, at the top. From this root, branches extend, leading to internal nodes, where further decisions are made, and eventually to leaf nodes, which represent the final outcome or prediction. Each internal node in the tree corresponds to a test on an attribute, or a feature of your data. For example, if you're deciding whether to play outside, an internal node might test, is it raining? The branches extending from that node represent the possible outcomes of that test. Yes, it's raining. Or, no, it's not raining. The tree learns by analyzing historical data. It identifies the most significant features that help differentiate between outcomes. This process is about recursively splitting the data into subsets based on these features, aiming to create increasingly pure groups with respect to the target variable. When an AI uses a trained decision tree to make a decision, it starts at the root node and follows the path down the branches. At each internal node, it evaluates a feature of the new data point. Based on that evaluation, it traverses the appropriate branch until it reaches a leaf node. The leaf node then provides the final decision or prediction. For instance, if you're classifying an email as spam or not spam, a leaf node might simply say spam, or not spam, having navigated through various email characteristics like sender, subject, and keywords. But how does the tree decide which feature to test at each node, and where to split the data? This is where concepts like entropy and Gini impurity come into play. These are measures of impurity, or disorder, within a set of data. Entropy, a concept borrowed from physics, quantifies the randomness or unpredictability in a dataset. If a node has high entropy, it means the data points within it are very mixed in their classifications. If entropy is low, the data points are mostly uniform. Gini impurity serves a similar purpose. It measures how often a randomly chosen element from the set would be incorrectly labeled if it were randomly labeled according to the distribution of labels in the subset. A Gini impurity of 0 means all elements belong to a single class. The goal of the decision tree algorithm is to find splits that maximally reduce entropy or Gini impurity, leading to the greatest information gain. It continually searches for the feature and split point that best separates the data into more homogeneous groups, making each subsequent decision clearer. This iterative process of splitting based on impurity reduction continues until a stopping criterion is met, such as reaching a maximum tree depth, having too few samples in a node, or achieving sufficiently pure leaf nodes. The result is a highly interpretable model that transparently reveals the decision-making logic, making decision trees a foundational and valuable tool in AI.